Welcome! In this explainer, we're going to take a journey deep, deep inside the digital brain of a computer. I mean, forget about the apps, forget about the websites for a minute. We're going right to the core of the machine. We're going to find out how it actually thinks. You know, how it crunches every single number, from a simple addition to the most complex stuff you can imagine.
Okay, so here's the game plan. We're going to start with the big picture, a simple computer. Then we'll zoom right into the CPU's calculating heart, the ALU. From there, we'll break down the 4 key jobs it has to do, and then finally, we'll get down to the nitty-gritty and see how the whole thing is built from the simplest little electronic switches.
All right, Section 1, inside a simple computer. Look, before we can really get our heads around the calculator part, we first have to understand the neighborhood it lives in. You know, what are the main parts and how do they all talk to each other? So at the very heart of any computer, you've got the central processing unit, the CPU. It's the brain of the whole operation. And that brain has 2 key parts. First, there's the control unit, which is kind of like the director, telling everyone what to do. And second, you've got the arithmetic logic unit, or ALU, which is our main focus. Think of it as the master calculator doing all the heavy lifting. All these parts, plus the main memory, are connected and talk to each other over this thing called the data bus.
So what even is a bus? Well, the best way to think about it is like a super highway for information. It's not just one wire, it's a whole bunch of them bundled together, and each wire carries one tiny bit of data. This is the physical road that connects all the important parts, letting them zip information back and forth at just incredible speeds.
And just like a real highway, this data bus has different lanes for different jobs. You've got the data lines. Those are the main lanes carrying the actual information, the ones and zeros. Then you have the address lines, which act like a GPS, telling everybody the exact location the data needs to go to or where it's coming from. And finally, you've got the control lines. They're like the traffic lights, managing the flow and making sure data doesn't crash. Okay, now that we've got the lay of the land, let's zoom in. Let's get to the real calculating core of that CPU. It's time to meet the star of our show today, the arithmetic logic unit. The ALU is where all the magic really happens. Seriously. It's this super specialized digital circuit, and its job is to handle 2 main things. All the math, we're talking addition, subtraction, the works, and all the logical decisions, stuff like and, or, and nor. Literally every single calculation your computer makes has to pass through this one unit. So how does this thing actually work on a basic level? Well, it's a machine built to do one thing really well. It takes in 2 16-bit numbers, performs a single operation on them, and spits out one 16-bit result. You can see here, one number comes from a little holding area called the memory buffer register, and the other comes from a special spot called the accumulator, which is basically holding on to the answer from the last calculation. But, right, how does the ALU know what to do with those 2 numbers? Well, the control unit sends it a very specific binary command, what we call an opcode. Now, what we're looking at here are the instructions for a simple model computer called Marie. And for anyone studying for an exam on computer architecture, you know Marie is a perfect way to learn these core concepts. In this case, its ALU is built to understand 4 basic opcodes, one for add, one for subtract, one for and one for nor. Okay, so let's get into the nitty-gritty. Section 3, the ALU's 4 operations. How does it actually pull these off? How does it turn a string of ones and zeros into actual math? And here is the first absolutely brilliant trick of computer engineering. It turns out computers are kind of lazy, but in the most efficient way you can imagine. They don't actually have a separate part of the circuit just for subtraction. No way. Instead, they figured out how to turn every single subtraction problem into an addition problem. And they do this with a clever little math trick called 2's complement. So to subtract a number, the ALU doesn't need a whole new subtractor's circuit. Instead, it takes the number, flips all its bits, so zeros become ones and ones become zeros, and then it adds 1. That new number is the negative version. And then it just adds it to the first number. It's this super elegant solution that saves a ton of space and complexity on the chip by just reusing the addition circuit. Now, this is really important to get straight. There's a big difference between how the ALU handles math versus logic. For addition, all the bits are connected, right? A carry the 1 from one column absolutely affects the next column, just like when you do math on paper. But for logical operations like and or nor, each pair of bits is handled all on its own, completely independently. It's like having 16 tiny separate operations all happening at the exact same time with no connection between them at all. All right, for our final section, we are going microscopic. We're zooming all the way down. How do you even build a circuit that can do all of this incredible stuff? Well, it all comes down to these tiny little switches called logic gates.
And the engineering principle here is it's beautifully simple. You don't try to design this massive, complex 16-bit calculator all at once. That'd be a nightmare. Instead, you focus all your energy on designing one perfect little circuit that can do all the operations on just a single bit. And once you got that, you just copy and paste it 16 times and wire them all together.
And you can see that exact principle right here in action. On the left, that's the symbol for a simple AND gate, one of the absolute fundamental building blocks. And then on the right, you can see that exact same symbol being used as just another component inside the bigger, more complex diagram of our 1-bit ALU.
So, how does the ALU actually choose which operation to use at any given moment? It uses a clever component called a multiplexer, or just MUX for short. The best way to think of it is like a set of railway switches. The opcode, that binary command, comes in and tells the multiplexer which track to open, physically sending the flow of electricity to either the part of the circuit that does math or the part that does logic.
And this brings us to a really, really crucial point. That binary opcode isn't just passive data. No, it is an active command that physically reconfigures the hardware in real time. When the ALU gets a 0011 for add, it literally flips internal switches to send the electrical signals down the addition pathway. For that one tiny instant in time, the instruction itself becomes the architect of the circuit. It's amazing.
And that kind of brings us to the final big question, right? We've just seen how simple on and off logic can literally perform mathematics. So what does that tell us about something way more complex, like powering an AI or running a cutting-edge video game?
Well, the answer is in the journey we just took. Every one of those incredibly complex tasks gets broken down and down and down into an absolutely mind-boggling number of these simple, lightning-fast hardware operations. It really is all just math and logic, happening billions of times every second, scaled up to a level that feels like pure magic.